Hello and welcome to Gravitational Fields Lesson 3A. Today we're going to be talking about potential energy. Now this is something you've been dealing with since you were about 11. You've heard of potential energy, specifically gravitational potential energy. We've got an idea of it. When we lift things up, they gain it. When they fall, they lose it, and that's normally turned into kinetic energy. So we've already got a basic idea of what it is. What we're going to be doing today is really delving into potential energy, trying to understand what it is, and trying to also place it within the idea of fields. So, we understand that if you take a mass and you lift it up, it's going to gain gravitational potential energy. And if you drop it, it's going to lose gravitational potential energy. So we already know that masses have it. So something to do with mass has to be in there. But there's also going to be gravitational fields as well. If you think about an asteroid in deep space, does it have any gravitational potential energy? Not really, no. There aren't any gravitational fields there. So somehow it's interaction between mass and the field that gives us our GPE. Now it's actually defined in quite a strange way. It's defined thusly. The amount of work, which would make sense because it's a form of energy, so work would go in there, it takes to move a test mass, which as we've already discussed is just a small mass that's going to be acted on by the field, from infinity to that point in the field. So that's a bit of a mouthful, don't worry, we'll go through that. So what does that mean? It means if I want to work out how much potential energy there is in the field at, say, this point, I've actually got to take a mass all the way to infinity, and by infinity we just mean so far away we count as being outside the gravitational field of the Earth. And then we're going to move it from infinity all the way to this point and see how much work that took. And then we define the potential at that point in the field as that amount of work. But there's a problem, which is it going to take work to move a mass from a long way away to this point? The answer is gravitational fields. No, it's not. They're attractive. So actually, the field's going to do work on the mass and pull it closer and closer to this point as it goes from infinity. Imagine something in deep space. It would be captured by the Earth's gravitational field and pulled inwards. So how do we get around this? Well, we define them as negative. Because rather than you having to do work on the field does work on the mass. So all gravitational potential energies are negative. This is so important. This comes up again and again. Whenever you see gravitational potential energy, it's defined as a negative, which is weird. Don't get me wrong, negative energy is not something we really think about very much, but as we delve deeper into this, it will work out, and the maths actually works really nicely. It's just a little bit strange off the bat. There is a very common exam question that comes with this. This question is, why is all gravitational potential energy negative? It's normally a 4-marker, so what I'd like you to do is I'd like to answer that question, and only after you've actually written it down, don't just think it, commit it to paper, then watch the next video and see how many of those 4 marks you got. Really try and get all 4 marks. The question is, why is all gravitational potential energy negative? Have a go. I'll see you in the next video.